In the last lecture, we had met scalar operators and tensor operators, which we had created out of inner and outer products of vector operators. Of course, we then went on to say a tensor operator is anything, any set of 9 components or any set of 9 operators which transform under the rotation of coordinates like the outer product of 2 vectors. And we had also seen that these 9 components of what are called Cartesian tensors of rank 2 form an invariant subspace under rotations. That is, if you take any linear combination of these operators, rotate your coordinate system, the resulting operators are going to be another linear combination of the same 9 components. So the subspace formed by linear combination of the 9 components of a Cartesian tensor of rank 2 is an invariant subspace under rotations. However, we had also seen that this subspace is not irreducible, in the sense that within this subspace there are smaller subspaces which are themselves invariant under rotations, which means that they don't mix with the other elements in that subspace. Of course, the trace which you form by just adding up T11, T22 and T33 turns out to be a scalar. It does not change when you rotate your coordinate system, so it does not mix with other operators. The antisymmetric part Tij minus Tji by 2 is also invariant. That is, the antisymmetric combination, if you rotate your coordinate system, stays always an antisymmetric combination. And here you have only 3 independent pieces, A12, A13 and A23. A21, A31, A32 are just negatives of these. So we have a 3-dimensional invariant subspace. And if you leave these 1-dimensional and 3-dimensional pieces out, you have a subspace formed by the linear combination of 5 components of the symmetric traceless part of Tij, and this in itself is also invariant. So remember, we formed Cartesian tensors by taking direct product of vectors. So that's basically the direct product of a 3-dimensional space with another 3-dimensional space. So you have 3 times 3, that's 9 of course, but this decomposes into 3 irreducible pieces, a 1-dimensional one, a 3-dimensional one, a 5-dimensional one. In the end of the last lecture, I had pointed out that there is an uncanny similarity between this result and something that you have already seen from addition of angular momenta. Of course, in addition of angular momenta, you don't really see 3 times 3 equals 1 plus 3 plus 5, at least not directly. What you see is when you add a 1-dimensional spin 1 to a spin 1, j equal to 1 to a j equal to 1, which remember are both 3-dimensional subspaces, you end up with a 9-dimensional direct product space which decomposes into 3 invariant subspaces corresponding to j equal to 0, j equal to 1, j equal to 2, which in turn form or generate a 1-dimensional, 3-dimensional and 5-dimensional subspace respectively. So it seems that the combination of outer product combination of vectors sort of form the same kind of basic rule as addition of angular momenta. And I asked you at the end of the last lecture, is this an accident or is there something deeper behind it? And of course the reason why I asked you this question should be obvious. There is a deeper reason behind it, and we are going to explore this deeper reason in this lecture and perhaps in subsequent lectures. So first, to see this, we are going to talk about spherical vector operators, and to understand this, let us start with the operator Vz. Now we already know where Vz of course is a z component of a vector operator. We already know that by virtue of being a vector operator, Vx, Vy, Vz have definite commutation relations with the angular momentum operators Jx, Jy and Jz. In particular, the commutator of Vz with Jz is just 0. That's fine. But now, let us do something. Let us look at the commutation relation which between J plus minus, the raising and lowering operators in the angular momentum algebra, with Vz. Well, J plus minus commutator with Vz is straightforward. J plus minus of course is Jx plus minus Ijy, and the commutator with Vz is easy to find out. It has two pieces. One is the commutator of Jx with Vz, which is of course Ih cross Vy with a minus sign, xzy being anticyclic. On the other hand, Jy with Vz is Ih cross Vx, and that I together with this I which is sitting here in the definition gives a minus 1, and that converts the plus minus here into a minus plus. So if you take the minus plus common out along with the h cross, what you get is minus plus h cross times Vx plus minus Ivy. Now what we will do is we will borrow a leaf from what J plus minus does to Jz eigenstates. J plus minus raises the Jz eigenvalue by plus minus 1. And as you will soon see, this is actually quite prescient of me, but that's of course hindsight. What I will do is I will define a set of three operators V0, V plus 1 and V minus 1 by this. V0 is our very own Vz operator, but these two combinations that we get when you apply J plus minus on V0, apart from the h cross factor and with an additional root 2 thrown in for reasons that will be clear very soon, these are what you call V plus minus 1. Notice that V plus minus 1 has a minus plus sign in front of this, and I must confess that when I first read about spherical vector operators, I was rather confused with this minus plus sign. That is, I would have thought that just like J plus minus is Jx plus minus Ijy, V plus minus should be Vx plus minus Ivy, and I could not really fathom out the reason behind there being a minus sign in front of V plus 1. The 1 by root 2 I could live with. It's just an additional factor which you throw in to make later calculations easy. Well, the real reason why you have minus plus sign here is that this is exactly what you get when you take commutator with J plus minus with Vz. You do get a minus sign for J plus and plus sign for J minus, which is the reason for the sign here. Well, what is the point? The point can be easily seen if you try calculating the commutator of Jz with V plus minus 1. And this is a pretty straightforward calculation which you should be able to do yourself, and the answer is plus minus h cross V plus minus 1. So this should begin to look similar to something you've already seen. That is, notice Jz's commutator with V plus 1 is plus h cross times V plus 1. Jz's commutator with V0 is 0 times V0. Jz's commutator with V minus 1 is minus h cross V minus 1. And just to make the point, let me just throw in these relations. Jz acting on the three states 1, 1, 1, 0, 1, minus 1. So when Jz acts on 1, 1, you get 1, 1 back with h cross. Notice that here when you take Jz's commutator with V plus 1, you get V plus 1 back with the same factor plus h cross. Jz acting on 1, 0 gives you 0 times 1, 0. Jz's commutator with V0 is 0 times V0. Jz's action on 1 minus 1 gives you, sorry, this is a sign error, this should be minus h cross. So this of course obviously is a typo which came in from cutting pasting too much. This is a minus h cross here, and jz v minus 1 is minus h cross v minus 1. So apart from this typo that you have here, you should realize that these two relations are uncannily similar. Here you have the action of the operator on a state giving you back the same state with a multiplying factor. Of course, these states are eigenstates. Here you have a commutator acting on v plus 1, v0, v minus 1, returning you the same states with the same factors. So this looks very much like an eigenvalue equation, except that v plus 1, v0, v minus 1 are not vectors on which the operator acts. They are operators on which you are taking a commutator. Then the similarity gets even more striking. Look at what happens when j plus commutator is taken with v plus, v0 and v minus. Now this is a calculation that you should definitely do yourself. Calculate these commutators, you will find that the results are these. And if you remember your j equal to 1 theory, the theory of spin j equal to 1, this should immediately look very similar. J plus acting on 1 1, after all 1 1 is the highest weight state, you can't raise the m value any further, is 0, just like this is 0. J plus 1 0 is root 2 h cross 1 1, which is what you have here. This should actually tell you why you put in a 1 by root 2 in the definition of v plus 1 and v minus 1. Of course, these are v plus 1s. I will sometimes write v plus or v1, but I really should be writing v plus 1 here. And j minus is commutator with v plus 1, v0, v minus 1 are again very similar to what j minus does on the states 1 1, 1 0, 1 minus 1. So there is an uncanny similarity between jz's action on the states 1 1, 1 0, 1 minus 1. There are 3 of them, of course, and these 3 operators, v plus 1, v0, v minus 1, how they respond when you commute them with jz and j plus and j minus. The similarity, of course, is total, except of course for the fact that here is an operator acting on a state, and here you are taking a commutator between 2 operators. But this can actually be made into almost identical, this nearly identical action can be made into almost identical by introducing a new notion, that of a small add map. We are going to come to that soon, but well, the important thing is this similarity between the commutation relations of the vector operator components v plus 1, v minus 1, v0 with jz, j plus minus on the one hand, and the action of the jz, j plus minus operators on j equal to 1 eigenstates on the other hand. This is not an accident at all. Well, firstly, let us note that just like states mix among themselves under rotations, so do operators. The vector operators mix with each other under rotations. And notice that linear operators form a vector space of their own. Now this is a different vector space than the one we started with. The states form a linear vector space. This is basic quantum mechanics. The basic idea is that the central thing in quantum mechanics is superposition. So if you superpose any 2 states, you get another state, which is where the linear vector space structure of quantum mechanics comes from. Now you must have heard this, and I'm pretty sure some of you know this properly, that the basic mathematical structure underlying the states of a quantum system is what is something called a Hubert space. It's a special kind of vector space which is a complete inner product space, but those technicalities are really not important right now. It so happens that operators which act on a vector space can be themselves linearly combined, right? That's something which you all know. You can add operators, you can also multiply operators by scalars, and it is very easy to check that under these operations, the set of all operators, linear operators acting on a vector space, they form a vector space of their own. Now it so happens that the linear vector space of operators acting on a Hilbert space turns out to be, or rather bounded linear operators acting on a Hilbert space turns out to be a Banach space, not a Hilbert space. Right now the distinction between Banach and Hilbert is not really very important. We essentially, all we really need is a set of all linear operators form a linear vector space on its own, and the vector operators, or the three components of a particular vector operator, they form an invariant subspace in this space, in the sense that when you rotate your coordinate system, operators of course mix among each other. After all, you start with an operator, you get a new operator. But if you start with any linear combination of three components of a vector operator and you rotate your coordinate system, the operator changes into a linear combination of the same three vector operator components. Of course, that is exactly what we had defined vector operators as, things which transform in the same way as coordinates do under a rotation of coordinates. Of course, you know that the transformation which acts on operators is O goes over to O prime. This is a picture where kets don't change as the operators do, and if the kets had changed under un theta, the operators change under un theta inverse O un theta. Now this is a transformation which changes the operator, linear operator O to a linear operator O prime. It is very easy to check that if you were to replace O by a linear combination C1 O1 plus C2 O2, the resulting thing will be a linear combination of the individual results. And this means that what you have here is a linear operator which is acting on the set of operators themselves. So this transformation of an operator to another operator can be thought of as an operator acting on operators. Just to distinguish this and make it easier to follow which set we are talking about, we are going to call such operators which act on operators super operators. This is not really standard terminology, but it should help us to understand which one we are talking about at which stage. So operators act on states of your vector space in a linear fashion. They themselves form a vector space, and the operators which act on this vector space, the vector space of operators, are what we are calling super operators. And the transformation O to O prime under a rotation of coordinates can be described by a linear super operator. And what happens when you carry out an infinitesimal transformation or infinitesimal rotation of coordinates? Well, the even theta operator is replaced by its infinitesimal version. Of course, this is ordered epsilon. There are ordered epsilon square corrections, and the inverse is simply this, which is easy to figure out just by seeing that if you drop the O hat from the middle, the product of these two will be identity up to ordered epsilon. Or it's even easier to figure that out from the fact that the inverse of a rotation through an angle epsilon about a particular axis must be a rotation through an angle minus epsilon about the same axis. Okay? And if you carried out this product, remember you are allowed to only carry this out up to order epsilon, you get O hat, which is identity, O hat identity. These are really identities and not one. And then you get first order terms from this acting on O hat times identity, or identity acting on O hat times this. And it's very easy to combine them and see that the result is the original operator O minus I epsilon by H cross times the commutator acting of n hat dot j on O. So compare this with what happens to states. What happens to operators is the operator changes by this piece, which apart from the I epsilon by H cross and a minus sign, which is different, is just a commutator with n hat dot j. For a state under infinitesimal rotation, you have this. The state changes to the original state plus I epsilon by H cross, a first order term with n hat dot j acting on state. So apart from the minus sign, which will give us some changes later on, the result of what happens when you rotate your coordinate system in the picture where kets change is very similar to what happens to operators in the picture where operators change. In one, the ket changes by a piece which is essentially n hat dot j, the angular momentum operator component in that direction acting on the state psi. In the other, minus I epsilon by h cross commutator of n hat dot j with the operator O. So, in a way, the commutator with an operator of the angular momentum component replaces the action of the angular momentum component on a state. So, with this background, it should really become clear why we had what we had in the last slide. The operators acted upon by commutators sort of mimicked states acted upon by operators directly. To make it even clearer, we will make a small detour into some bit of slightly more advanced linear algebra. We are going to talk of two maps, small add and big add, which map operators to super operators. This detour is strictly speaking not absolutely necessary to understand what's going on, but with this detour it's going to make a lot of terminology very much clearer, and it's worth looking at this. Later on, when you go on to study Lie algebras, the small add and the big add map, Lie algebras and Lie groups, the small add and the big add map are going to play a very big role there. So for the time being, for this course, what I'm going to say in the next couple of slides or so is not essential, but may help in understanding. So let's go on to that.